Hey, hello, welcome. My name is Dr. Phil Winder and I'm the CEO of Winder AI. If you haven't watched any of these videos before, then welcome. We present lots of juicy technical talks about various AI topics because we're specialists in AI and ML. We provide consulting and development services across the AI spectrum from traditional data science all the way through to AI agents. Just before we get started, a little bit of admin as always. We've got comments on YouTube videos and LinkedIn. So if you're watching this video live, then please feel free to post a comment, and I should see it pop up in my studio here. Yeah, if you need any more information about what we do, or if you're interested in any other talks that we do, then check out our website, which is winder.ai. Yeah, lots more events coming up, so check it out. Okay, today's topic is all about vision RAG. And this is a really interesting thing for me because the first time that I did this, I was genuinely quite shocked. I was quite surprised at how well it achieved the task that I set out for it. And I thought that actually, I haven't seen this talked about much in academia that well. No, he's talked a little bit about in academia. He's definitely not talked that much in kind of tech circles. So I thought I would produce a little bit of sort of basic, simple, a few simple examples to kind of demonstrate how it works. So yeah, so the whole topic of today is to describe to you what vision RAG is and go through the sort of the underlying fundamentals a little bit. I'll also give some tips on what RAG is in general and where you can find more information about that. We've got lots more on the website, so you can check that out as well. And then I'm going to take you through a little bit of a walkthrough of some really simple Python code. And it's not fancy, it's very simple, but it does the job. And I think that's probably the best way of understanding what's going on. And then I'm going to do another demo of a more production-ready system called Helix as well, which I'm involved in developing. Okay, let's crack on. So I'm just going to rearrange my face a little bit so you can see this diagram in slightly more detail. And of course, if you've got any questions, please feel free to reach out to me or type a message in the chat there. Okay, so got one question already. Thank you. Well, I'm not going to be talking about specific types of graphics. All I'm trying to do here is demonstrate how to work with, visual media and visual data. So hopefully you'll be able to take something from this, because there is a couple of examples and demos that I'm going to show with that content. So this is a depiction of a typical RAG process. So RAG, so let's start from the beginning, just in case there's any beginners here. So RAG stands for retrieval-augmented generation, and you can largely ignore the generation bit because that's handled by the various language models. Okay, so they're still responsible for generating the data. The important bit is retrieval. It's been shown in a wide variety of contexts that if you can provide relevant context in the initial user's query, then the performance of your system will be superior to that doesn't use any context. And when we say context here, what we're saying is basically more information. And that information can come from anywhere. So retrieval could be searching in a search engine. It could be searching a database. It could be searching all sorts of different kinds of things. And when people say RAG, they're typically assuming that you're working with a modality of text. So the idea is that you get documents somehow from somewhere. Could be a wiki, it could be a book, it could be PDFs, it could be emails. And then the next step in the process is to chunk up that data. Chunking is important because you need to split up the text into small semantic snippets. So and that the definition of a good snippet is very dependent on the domain that you're working in. So a snippet could be a sentence, it could be a few words, it could be an article, it could be of any size. And then you use those snippets, and you feed those snippets into a special model called an embedding model. The goal of an embedding model is to take that textual content and convert it to a numeric representation. And that number, that vector, is supposed to represent that content. So you can imagine if you include too much in that snippet, then it kind of provides a very blurry average of that content. If you provide too small snippets, then it provides the numeric representation of an individual word potentially, which also is probably not that useful. So trying to find that chunking threshold is part of the development process. It's not easy to get right. Yeah, so then the embedding that comes out of the text embedding model is then stored into a database. So that again, people usually refer to them as vector databases, as if they are specialized towards working with vectors. But to be honest, just think of it as a database. Lots of normal databases support adding vectors to it, like traditional. We use pgvector and derivatives of various Postgres databases all the time because we're confident and used to running Postgres databases in production. But like picking from another domain, for example, Neo4j is a graph database, but it has vector embedding support. So it's not really a vector DB, but it's still useful. So think of that as a DB. So that is known as the indexing pipeline. It's going from raw documents through to storage of that vector in a database. When the user comes in and starts trying to leverage that information, the first thing that they do is provide a query. And again, that query isn't just a query, it's also the query plus any of the context that you can include inside that query, maybe past historical conversations. It could be metadata about that user, so on and so forth. That text is then converted into the same embedding space that you used in the indexing pipeline. And that's actually really crucial, because if you're using a different embedding model, then potentially those numbers are representing different things. So it has to be the same embedding model. And then you use that new the query embedding to search your vector database for all of the relevant documents. And eventually you'll get back a ranked list, and you need to incorporate that into the prompt, the final prompt for the generation model. So this step is called fusion. It's the idea of trying to fuse the results that you've received back from the vector database into a final prompt, and then that's passed off to the language model for final generation. Okay, so that is end-to-end process. If you'd like to learn more about all of that, it's things like different RAG architectures, different implementations, more basic what is RAG kind of articles, then you can find all of them on the Winder AI blog. Okay, just at the bottom there. So that's all well and good. But what happens when you start to receive content and you want to index content that is a little bit more complicated than just text? So the example I'm going to use here is some finance information, but infographics, Krishna, is a very similar set of data that you would work with. And as well, you can imagine maybe using slides, maybe using like a PowerPoint and like PDF slide decks. This same process would work in exactly the same way. So here we've got a wide variety of different types of information. We've got information that comes from text, information that comes from tables, and from images. And about a year ago, actually, is that right? Yeah, about maybe a year ago, there was a paper called by some Hugging Face folks that developed a procedure or a model called Colpally. And this is a picture from that. The link to that paper is at the bottom. Can I see 24/7? So yeah, it was just about a year ago, just less than a year. And they were talking about how you tackle this problem. And this is a picture from their paper that describes what used to happen. So previously, you would run some optical character recognition model over the top of that document to extract the text. Because remember, quite often this is scans of things. It's not the text sometimes isn't even embedded in the PDF. It's quite often a scan of something. Then you can start doing some fancy layout detection and try and detect if it's code, do this, if it's a table, do that, and have different chunking and methodologies for working with those different types of data. And then that gets passed into the text embedding model and everything carries on as normal, but didn't work very well for obvious reasons. So what they proposed was this idea of working with images, just work with images, because a lot of the information contained within PDFs are actually just images. So in the example I'm going to use later, this image at the top is a graph, a plot, but it is encoded as an image inside the PDF. Similarly, this table is not a formatted table of any kind. It is an image of a table. So this is also an image as well. So the vast majority of things are well represented by it being an image. And so maybe what we can do is we can train models to understand those images. We can use multimodal models to understand that, and try it that way. So in essence, this is a representation of the same indexing and querying pipeline, but now we're going to work with images instead of text. And I've tried to retain the same sort of format and the same stages to kind of highlight the similarity that's happening here. So again, we start off at the top left, the indexing pipeline with some documents. In this case, it's just a PDF or a set of PDFs. You could imagine this process with any other type of document like slides, PowerPoint, things like that. And we chunk that document up into segments, into image segments. So rather than looking in terms of like text now, we're thinking about trying to calculate embeddings over segments of images. So again, you need to think about your domain, your data, and pick a chunking strategy that works well for the types of questions that your user is going to ask, and also the type of data that you have at hand. In my experience, and in the demo here, a simple chunking of an entire page, i.e. taking a picture of a page, it works remarkably well. So we convert that document into images, and then we pass it to a specialized embedding model. This isn't a generic text embedding anymore. So you can kind of, for those that are more used to using RAG systems, you can kind of ignore the man plus crown equals king kind of depictions of what's going on. And now this is an embedding of something that you can see. So again, you might want to consider when you've got different types of data on there, like we have, like a plot and a table and some text, you probably want to separate those, because if you don't, we'll end up with an average embedding of all those three things, which is quite likely to be different. Another way in which it's different is that this embedding model that I'm using in the demo and in the code, which I'll show you later, has been specially trained to work on PDF documents. So this is where it could get a bit interesting for people like Krishna, who are looking for infographic related workflows. You may have to, if you can't find an embedding model that works for you, you may have to train your own embedding model on infographics. Everything from then on basically works in the same way. We store those embeddings in the vector database. The user query is the same. We use the matching embedding model again, but this time we're passing in some text rather than an image. And again, the fusion gets a little bit different as well, because we don't have text here. The fusion is inserting images into the context of the language model call. And this time we can't use a standard text language model. We have to use a multimodal language model, or effectively a language model that supports both images and text. As an aside, we say multimodal here. The multimodal models typically work quite well with audio and sometimes with video as well. So you can follow the same process for audio files and for video files as well. Okay, so that's what that looks like. So let's have a quick look at what that looks like in real life. So this is a demo dummy repo that I mocked up in Python. You can visit yourself, check out the code. I'm just going to give you a quick walk through the code as well now, but I'll just leave that slide up for a few more seconds. It's github.com/window.ai/vision-rag-demo. All right, let me try and share my screen. I'll just do my entire screen to make sure this doesn't break. Okay, perfectly. Is that working? Hopefully you can see this. Send me a message in the chat if you can't see this. I'll assume that you can. All right, so this is the README of the repository. If you want to run this code, you'll need a couple of prerequisites. Probably the first and the biggest one is you need a GPU in order to run these models. I've tried to pick smallest models I can find. Actually, let's go back. Let's step back a bit. Why do we need to run these models ourselves? So actually, the crucial element is the vision embedding model. There's basically no commercial provider that provides a visual embedding API. So, you know, no OpenAI, no Anthropic, no Google, none of them. And the easiest way to get started here is my preferred way of using this technology is secure, private, and flexible local models. And so to do this, I've attached my machine to I've SSH'd into another machine, which has an attached 4090 NVIDIA card that has 24 gigs of RAM, and that's enough to run the models that we need. Docker to run those models as well, and UV just to run the code if you're interested in doing that. There's 3 containers that we need to be running. First is pgvector. Pgvector is a derivative. It's basically Postgres with an extension. So it's Postgres with an extension that works, that enables vector search. So pgvector, there's lots of others as well, which are faster. Vector Chord is a faster implementation of this, but this is more popular, so I decided to use this. The next 2 are the embedding and the language models. So the first is the embedding model. We're using VLLM in order to host this model. You'll need to pass in your Hugging Face hub token in order to download the weights for this model. And the model we're using is a Qwen 2 derivative model. So it was originally a Qwen 2 language model, and it's been fine-tuned into an embedding model. And thank you, Mr. Light, for that model. Note the extra parameters that you have to pass there for this to work. And then for the language model, we're using Qwen 2.5 VL. This is the vision supported multimodal model from the Qwen team. Again, note this parameter here. This is absolutely required to make this work. By default, it effectively only allows you to pass one image in the context, which is not enough for our retrieval requirements. So you need to increase that to support multiple images. Interestingly, if you try this is a massive side note, if you try the Together AI API and try and pass an image to that, it will fail, it'll break with their multimodal models because they've not set this parameter. You can only send one image at a time. So if any Together folks are listening, then add that to your API, please. Okay, and then now we can start spinning up some code. So I've created a very simple Python click app. All of the code is in the CLI.py. It's got 3 methods, three CLI subcommands. We've got index, query, and chat. And I think it's best if I just go ahead and actually use it. It's probably the simplest way of doing it. So if I uv run, so index. Oh, why isn't that not? Oh, it's because I'm on the wrong machine. This is the SSH machine that I'm in. Okay, there we go. If I was to run a command of index, then this is the command I'm using to index in my PDF files. I'm not going to do that actually because I believe my database already has a couple of items. But basically what I've done there is I've passed in two PDFs, a PDF of a cat and a PDF of a panda. Let me see if I can show you them actually. It's probably worth seeing that. Here we go. So this is the first PDF. It's a very simple PDF. It's just a picture of a cat and a very simple PDF picture of a panda. This is kind of what I use as my dummy examples to make sure everything's working. So that's, I've indexed it with the index command. Now, if I run query, then it will reach out to the vector database. Oh, let me just check the questions actually. Yeah, all good. It reaches out to the vector database and it's returned 2 files, I believe. Let's add some JQ to that just to see it. There we go. Perfect. And I've returned the score that's coming back from the vector search. This is the similarity score. And I've also returned some metadata that was associated with that element in the some metadata for that record. And you can see that when I've queried for panda, we've got a score of 54 for the file panda and 35 for the file cat. If I change that query to cat, then you'll see that it's now switched around. We've got a higher score for cat. Let's see what happens when we search for dog. Okay, very, very similar scores, but it's just preferred the panda. Pandas are slightly more like dogs than cats are. So that's a very quick demonstration of the indexing pipeline and the querying pipeline. What I haven't shown you yet is the final step in the process, which is passing that information across to the language model. Hopefully I can, yeah, there we go. I've got an example in my history here. Ignore that first warning. It's just an annoying warning from the DB. And I've asked it basically, what can you see in these images? And it's saying the first image shows a panda bear sitting among bamboo leaves. And there you go. If we were to change that query, we can see these cat images, then it would probably weight the cat image first. The first image shows a wildcat. There you go. All right. So that is all well and cool. What does that look like so let's just very quickly review the code. So to mock this up, I used Haystack. Haystack is another, AI pipelining solution. It focuses more on the pipeline than it does like it focuses more on the pipeline than the tools and the methodologies. You could say that maybe like LangChain is focusing more on the techniques and the tools, whereas Haystack's kind of more at the pipeline level. So anyway, I used Haystack, and it consists of a couple of components. Okay, so that's the query pipeline. I'll come back to that in a second. Here is the PDF pipeline. We've got a bit of code that converts the PDF images to the PDF to images. So I think actually I've got probably a couple of these here. Yeah. So there you go. These are the images. You see they're JPEGs now. These are the JPEGs that have been created from that part of the pipeline. Oops. Then we've got a splitter to split up the multi-page PDF documents into multiple separate embeddings. Then we've got an embedding, which we've already talked about, and a document writer, which writes that embedding to the database. On the query side, we have an embedder that takes the text from our query and retrieves vectors based upon that embedding and then returns it to the UI. And then I think there's just a little bit of syntactic sugar in the chat function where, yeah, basically I'm doing that. I'm doing both of those things. I'm calling the query function here, and I'm then passing that to an OpenAI compatible API. But remember, it's this local model we're running. Another minor interesting thing is when you're working with images, they either need to be URLs, or, which is usually, this is more useful, they need to be base 64 encoded. Interesting. So I'm actually passing it as a data type of image PNG, but you just saw that these images are actually JPEG. So it still works, even though it's not quite right. Okay, yeah, so I think that's simple example. You can play with it yourself. It's simple enough to be able to understand. Try it with different images, try it with different PDFs, try it with your infographics, see if it works. I think you should be able to get that working fairly easily. Yeah, okay, so what's next? Let's go back to the presentation. Right, next. So I mentioned that was a pretty simple example. So now I just want to do a slightly more complicated version of that demo, but with some, more hardened software that we've created. So Helix ML is a secure, private LLM platform. It's intended for businesses and enterprises, multi-tenant authorization, UIs, all that good stuff that enterprises love. If you're working in an enterprise environment and you're looking for a private secure LLM solution to host on your own infrastructure, then that's exactly what Helix is for. One part of Helix is the ability to do RAG, and specifically vision RAG. So I've spun up a cluster that I'm going to test on. You can try your own clusters if you want, actually. If you go to, first just visit Helix ML and just learn all about it. But if you go to deploy.helixml, you can log in and spin up your own environment, your own Helix instance to have a play with. Takes a little while to set it all up, but it does work eventually. Oh, sorry, I've just realized that I'm not sharing my screen anymore. Apologies. Right, so let's just share my screen now. Window. Entire screen, I mean. Sorry, so I'll do that again. So yeah, what I was just going through there was, I was just taking you to deploy.helixml, where you can log in and spin up your own environment. And that's exactly what I've done here. So this is an instance of Helix. I've already logged in as just a test user. I'll just triple check that everything's working okay. Yep, okay, so that's all still working. Right, set up in this environment, if I just go to the dashboard, two inference providers. We've got an embedding provider, which is coming from this URL, which again, local, private, secure. And we've got the chat model that's coming from this URL. These two models are exactly the same as what we've just used in that Python code. It's the Mr. Light model and the Quen 2.5 VL. I have preemptively created a couple of apps in Helix. We tried to create this abstraction called apps. And in there, we have added some knowledge, and I've added some finance knowledge. So these are 4 PDFs that are available in the repo as well, which are quite complicated, some of them. Let me just take a quick look at that. Which one's the biggest one? That one, 2017 one, that one. So this one is yeah, quite a lot. Lots of infographics, lots of charts, lots of text, lots and lots of tables, and it's very big. So it's a really good sort of demonstration of what finance professionals are having to work with. But I've just indexed this as a pure text source. I've also created a second app, which I've called Beast Mode, which is provided both text and vision. So now I'm going to go ahead and try those apps, and I'm going to try and remember the query that so inside one of the documents, there's a document about, there's some research about how news articles correlate with stock, basically. And so I think I'm going to try and target that information. Like obviously, typically in a normal daily workflow, you might not be specifically targeting information, but let's give that a go. How does the energy market correlate with news? Let's try that. Okay, let's see if it's cited the document I'm interested in. It has. Excellent. Yeah, so this is exactly what I'm interested in looking at. Right, so that was just with the text. So what the text model has done is that it's pulled out some very generic information, and it's not really answered the question very well. There's a couple ones down here actually. All right, so maybe let's be a bit more specific. What is the I don't know. No, that might be okay. All right, let's try this with the other app now, with the vision embedding, and let's see how that fares with this. So now this is going away and it's checking both of those. They are fantastic. Oh, it hasn't shown the image. Oh no. Just show your cite your sources. Oh, interesting. I still don't know if that's actually the answer I was expecting, because that's still coming from the. I wonder if that is actually in the text. Maybe I've done a bad demo. Sorry. Right. So this is the table I'm targeting. Yeah, it is a value of 35. So I think it's giving me the right answer. Let's ask something about this plot. See if we can get what's the peak sum of sentiment deviation. What's the peak sum of for oops. Yeah, sorry. I don't think that's quite working. It's not pulling out the vision rag. Oh, well, that's what happens when you try and demo things that you don't test before you try to demo it. All right, let's just remove the text source and force it to just use the vision. Or we need to actually use that up now. Interesting. All right, I think somebody might have broken something, because it looks like it is indeed. Yeah, it is working and it is using the vision model, but unfortunately the citations have broken a little bit. So this previously, this used to show a nice thing at the side with images in it, and it's not at the moment. So I will check with my colleagues to see what has happened there. Actually, let's see in that previous answer what happens when I click that. Oh no, that is the full PDF. Interesting. Okay, well, we'll look into that. And yeah, the goal of that demo, at least, I think we can probably find a video of this elsewhere on the internet, but the goal of this was to demonstrate that vision models and vision embeddings are capable of embedding, quite complicated information, like all of this numeric information that's contained within image, graph information. I think actually what's interesting when I try and use this is that you start to struggle to actually pose the question a little bit. It becomes quite hard to describe what you mean by peak value or top of graph. So I think that's something that somebody could think about, actually, because I think that's quite an interesting research problem. We don't really have the language tools available to query images very well. So anyway, that's yet another aside. Okay, let's go back to the presentation again, and start to wrap up, because yeah, I've kept you for over 30 minutes already. Hope you learned something today. Hope you enjoyed it. Apologies for the breaking demo there, but the demo gods were not quite on my side today, unfortunately, but hey ho. If you're interested in signing up to find out about more events and more articles and lots of other things in between, then if you could browse to any of the pages at the bottom of the Winder AI website, you can see this sign up for our newsletter page form that you can fill in, and we'll send you all lots of goodies out. And yeah, to conclude, Vision RAG is very familiar. The patterns the patterns are very similar to traditional RAG, or you can at least massage them into very similar patterns. So it should be fairly easy to adopt. Fascinating thing here is open source models lead the way. Like you have to use open source models if you want to enable this functionality. You can't use a third-party API to make this work. But there's very much yeah, I gave some Python code and it works reasonably well, but there is obviously a lot more to it than that simple example. Very much like the meme, like draw the rest of the owl. It's very much like that. So everything from choosing all of your chunking parameters all the way through to running sort of production databases and things like that. As you've seen, in the production software, someone has changed something and something's not quite working as it used to. All good fun. So if you're interested in getting something like that more out of the box, then check out Helix. It's under active development now, and we'd love to get your feedback, especially if you're working for an enterprise, so you can reach out to us there. All right, I think I'll call it a day. My name is Phil Winder. My email is phil@winderai. If you have any AI projects that you're interested to talk to me about, then yeah, definitely reach out to me, and I will see you next time. Thanks a lot. Bye-bye. I'm just going to hang on for 2 seconds just to see if there's any extra questions that pop up. Okay, no, thank you, Krishna. Appreciate the comment. And no more questions, I don't think. So I will catch you all another time. Thanks a lot. Bye-bye.